Previously, we showed that the ideal gas law can be written as PV equals nRT or PV equals capital N kBT. This ideal gas law works when our densities are low enough that the volume effect of molecules is not significant, and also the long distance interaction between molecules is also not very appreciable. This is supported by a number of different laws: Charles's law, Boyle's law, the Gay-Lussac law, Avogadro's law. When we put them all together, we get the ideal gas law. Okay, so it is supported by experimental evidence, and it does work under certain approximations. In this section, we're actually going to show that you can use very simple mechanics to also derive the ideal gas law. And again, we make a few assumptions like we did before. We make the assumption that there's no long-term interaction between the molecules. So that's going to prevent us from having phase transitions here. And the molecules themselves really don't occupy any significant volume. So let's look at this. We're looking at basically taking a bunch of particles in a box, particles that act like points, and we're going to let them collide with the sides of the walls. The force of impact is what's going to provide the pressure. We know pressure is force divided by area. We know that force is equal to the change in impulse divided by the time. Okay, we can put this all together again using the different principles that we know of mechanics to come up with the expression PV equals nRT, PV equals capital N kBT. Okay, so let's take a look at, let's start with a particle in a box. And here we have this particle in a box. It's bouncing around. It has some mass m. And throughout this approximation, or throughout this model, we're going to use molecules all of the same mass. So this is homogeneous. We have this molecule moving with a velocity v, that's a vector, and we're going to consider only the x component because it is the x component of the velocity which is going to transfer momentum to one of the walls, which is in the normal direction of the normal direction of x. So again, we will then extend this to all three dimensions and to many particles. So again, here's our particle. We are most interested in this wall right here, and we are most interested in the x component of the velocity. Okay. Now, we're dealing with a cube which is a dimension d by dimension d by dimension d. So honestly, if we're to diagram this entire container, it would look something like this. This wall would be d, this wall would be d, this wall would be d. So the diagram that I have here actually has it a little bit extended in the x direction. So just ignore that for now. But let's talk about a particle bouncing back and forth. And again, we are interested in the particle hitting this wall right here, colliding with it, and then bouncing off. So again, let's remember back to our idea of impulse. Impulse is equal to the change in momentum. It's also equal to the force divided by the time. So we have this particle coming in. We're only considering the x component of the velocity for now. It comes in with some momentum, negative mvx. Okay, it's traveling the negative x direction. And after it collides, it's going to bounce off and have a momentum of mvx. There's no energy loss. This is an elastic collision. Okay, if we look at in total what the impulse is, the impulse on the wall, we are going to have a total impulse of 2 mvx. basically, again, comes in with the same kinetic energy that it goes out with. So it comes in with negative mvx in momentum, bounces off with positive mvx, transferring momentum. So the force on the wall, by what we know by impulse, it's another version of Newton's second law. We know Newton's second law is F equals ma, but Newton's second law also states that the change in momentum over time is equal to the force. So we are going to experience on that wall an impulse of delta px, okay? And this is going to happen every round trip that the particle makes. So it's going to hit the wall, bounce off, and then come back after traveling a distance of 2d, okay? So delta t represents the round trip of this particle. Again, hits the wall, bounces back, hits the wall again, bounces back. And we need this delta t because the force isn't constant. The force is only going to be present when the particle is hitting the wall, okay? But if we want the average force, and the average is what's important here because you've got so many particles in our final analysis hitting the wall at any one time. So everything's going to average out over time. The force is going to be constant of a number of molecules hitting. But the average force for this one particle hitting the wall is going to be the change in momentum divided by the time it takes before it hits the wall again. So I put that all together. And again, we know that velocity equals distance divided by time. It travels 2d over delta t. Okay, distance divided by time, round trip, 2d, the distance one way is d. And therefore, delta t equals 2d divided by v. So I'm going to take this, I'm going to plug that in right here. And it becomes fairly obvious that we can get rid of a few things. The 2's cancel out. This v is 1 over vx, which is just vx. So that vx becomes a squared up here. And our final expression for the average force is mvx squared divided by d. Well, that's hopeful, right? Because remember earlier on when we had a discussion, we said that temperature was proportional to the average kinetic energy of the molecules. And here I have something that looks very much like kinetic energy, mv squared. I know kinetic energy is 1/2 mv squared, but mv squared is proportional to the force. Force is proportional to pressure, right? Pressure is force divided by area. So we see that there's going to be a relationship between the temperature, okay, and the force on the walls, which of course is related to the pressure on the wall. So we're getting closer to this ideal gas law. So let me take that expression again, and I've just basically written out the whole thing over again, that force is equal to mvx squared divided by d. And now I'm going to extend this idea to making many particles. Oops, let me just change that. Many particles hitting this wall and applying their own force, okay? So F1 represented the force due to one particle, but maybe you'll have a second particle, third particle, all the way up to Fn, okay? For n number of molecules that are trapped inside this box. So now my expression becomes, instead of mvx squared divided by d, it becomes mvx1 squared, vx2 squared, vx3 squared. You know, I have many different particles all the way up to the nth particle. Okay, I filled my box up with n particles now. So the total force on the wall is going to be this new expression right here. Okay? All right. Now, again, we are not interested so much in what one particle is doing at any one time. We are interested in the average effect of all the particles. So what I can do here is make another substitution. I can say, and this is very common when we're dealing with thermal physics. We're dealing with the large study of a statistically significant group of molecules. We're interested in the total effect. Again, what each particle is doing at any one time isn't important. It's the average of all the particles. So if I look at this right here, and bear with me for a second, because we're not taking the average speed and squaring it. We are squaring all the speeds of each molecule, the first particle, the second particle, all the way up to the nth particle. We're squaring all those speeds. Again, it's very much related to their individual kinetic energies. And we're going to take the average of the squared velocities. Okay, anytime we take an average, notice the average or the mean is over the v squared. Okay, it's not squaring the average, it's taking the average of all the squares. And anytime we take an average, we take the sum of all the individual numbers and then divide it by the number of items that we're averaging over. So I'm going to replace this part of the equation, this part right here, which identifies each individual particle all the way up to the nth molecule. And I'm going to replace that with this concept of Vx squared average. Okay, so now that's going to be inserted where we had that. And our new expression becomes this. This is the force due to n particles on average. Okay, and again, we only have a force when the particle's actually hitting, but if n is really, really large, okay, n is really a large number, I should say, greater than 1, much greater than 1, maybe Avogadro's number, 10 to the 23rd power. Any fluctuation is going to be averaged out. Particles are hitting the wall at any moment, at any time. Okay, so I have my expression for the force on that wall, okay, due to n particles. All right, here's where it gets a little bit tricky. Vx only represents the velocity in the x direction, okay? This is going to seem like it's a little underhanded how I do this, but we know that when we take the magnitude of a vector, such as velocity, okay, we do in 2 dimensions, we have Vx and we have Vy, okay, and V squared equals Vx squared plus Vy squared, okay? It's basically just Pythagorean's theorem. If I have a vector in 3 dimensions, okay, x, y, z, and I'm writing this vector out, again, let's say I have v, okay, it is going to be Vx plus Vy plus Vz. I'm sorry, it's going to be Vx squared plus Vy squared plus Vz squared, square root. So here we say V squared equals Vx squared plus Vy squared plus Vz squared. It's just another version of Pythagorean's theorem, except for in 3 dimensions. I know, Pythagorean's theorem is for a triangle. However, if you do this construction properly, it's actually 2 triangles that are put together to get to this. But in any case, I have no reason to assume that the molecules are moving faster in 1 dimension than in a different dimension. Okay, so if on average my molecules are moving 350 meters per second in the x direction, my expectation is we're also moving 350 meters per second in the y direction and in the z direction, okay? It's isotropic, which means it's the same in all dimensions. You can't really get many systems where it's going to be faster in the x direction than the y direction and the z direction. So I can now say, all right, v squared average is equal to vx squared average plus vy squared average plus vz squared average. That's what I said before. But if vx equals vy equals vz on average, okay, I can just make a substitution here. Here I have vx squared average. I'm going to replace vy squared average with vx squared average. They're all the same. They're equal. I'm going to replace vz squared with vx squared. So I have 1, 2, 3 times vx squared. So what this is essentially saying here is the velocity squared on average, okay, is 3 times the squared velocity in the x direction on average, okay? It's just taking into account that the particles are also moving in the y direction and the z direction, okay? So, you know, essentially this makes sense, think about it, that the overall magnitude of velocity is going to be greater than just the velocity in one dimension, okay? So by accounting for all 3 dimensions, we get rid of vx, okay? And now we have 1/3 the average, the velocity squared on average, okay? So again, just remember what we're doing here. V squared, okay, V squared represents the velocity squared, the magnitude of the velocity squared or the speed squared, okay? We are taking the average of all the V squareds, okay? It's very much related to the kinetic energy of each individual particle, if you want to think about that. So it's sort of like related to the average kinetic energy of each particle. So now I'm going to plug this in right here, okay? And of course, I've got to take a look at the force on one individual wall. Again, you know, we've got to, I think I have a little bit of a problem with this one right here. I've n particles, so it's going to be n times m over d. But in any case, I make that substitution here, and the force on one wall due to n particles is going to go by this equation right there. Okay. Now, here's my equation. The force on one wall. I've got to remember what I am looking at. My container is actually a cube again, okay? And the dimensions of the cube are d by d by d. So 2 things. The area of one wall is d squared, right? So when it hits one wall, that force is distributed over an area of d squared. The total volume of the container is d times d times d. So that's d cubed, okay? So I'm going to make some more substitutions here. First of all, I'm going to define my pressure. My pressure is my force, okay, divided by my area, which is d squared. All right, so now my pressure is this equation right here. But notice I can put this d together, that's from my force equation, with the d squared for the area, and now putting it all together. So this d and this d are going to become v, okay? you become d cubed, which becomes v. My expression becomes this. 2n over 3, I'm going to pull the 1/2 out here. That's where the 2 came from. Okay, 2 times 1/2 is 1, so I can do that. That's going to allow me to express this part of the equation in terms of something that's close to kinetic energy, 1/2 mv squared. Okay, again, this is not the kinetic energy of one particle. This is the average kinetic energy of all the particles. So I'm going to be able to get, substitute in here. My v is on this side of the equation because we have 1 over d cubed. I'm going to move it to the other side of the equation. And isn't this great? It's now starting to look like the ideal gas law. PV equals 2/3 n 1/2 v squared on average. Okay. What's kind of neat is I can basically identify all my different parts here. I need to get to PV equals capital N KB T, right? That's where I need to be. So I'm going to pull out KB and say, okay, looking at this whole thing, KBT must be equal to, here's a 2/3, okay? Here is my average kinetic energy, 1/2 mv squared. So my KB is going to be equal to 2/3 1/2 mv squared, KBT. All right. So that becomes again, I think I see another problem. Okay, no, 2/3, 3/2, 3/2. So many numbers here. 1/2 mv squared on average. Okay, and then we can just see that 2/3 KBT is equal to the average kinetic energy. Okay, so this shows two very important things. One, we've pretty much arrived at PV equals NKBT, okay? And if you're more comfortable, you can write this as PV equals, make that substitution for moles and R and T. That's fine if you want to do that. But the other thing that we see is for the first time, we could see a relationship between temperature and the average kinetic energy, okay? And of course, the average kinetic energy is equal to 3/2 kBT. If you want to look at the total kinetic energy of a system, the total kinetic energy is 3/2 number of moles times RT. Also, we could obviously write this as 3/2 big N kBT, okay? So again, this is the average per molecule. If we multiply it by the number of molecules, then we get back the total energy. So, this is really remarkable. The ideal gas law, we can get it by doing enough experiments at low density and seeing all the relationships between pressure, temperature, and volume. But we can also derive it just using simple Newtonian mechanics. And that's really, I find that remarkable. So for a monatomic gas, the kinetic energy is the only type of energy that the molecules can have. And since it's just translational energy, we say the total internal energy of the gas is going to be equal to the translational kinetic energy on average times the number of molecules, which is 3/2 nRT. Or again, if you want to use a Boltzmann constant, 3/2 big N kBT. Both of them work. All right. Now, you're going to see this pop up a few times later on. There's something called the root mean squared speed. Okay, it gets really confusing because there are so many different speeds that we can talk about when we're talking about a gas. Okay, there's the speed of sound, which I think is most closely related to the average speed. There's the root mean squared speed, which we're calculating right here, and there's also the most probable speed. So when we talk about a gas, we can be talking about three different things. Now, going back to this equation right here, okay, again, that 1/2 v squared on average is equal to 3/2 kBT. We can solve for v here. What I'm going to do is I'm going to multiply both sides by 2, so sort of get rid of that right there, and we get that v squared on average is equal to kb t times 3 over m, and then we're going to take the square root. We're going to take the square root of both sides and get an expression for just the RMS. See, we have to call it RMS because we've already taken the mean, root mean squared speed here. So again, that gives us this expression right here, which again is a little bit hard to think about, physically what's happening here, because this is not the average speed. It actually represents a square root of the average squared speed. And if the distribution in molecules was completely symmetrical, meaning that there were just as many molecules moving faster than the most probable speed as moving slower, then the mean and the root mean squared would be the same. But we'll see later on that there's a distribution there. Okay, but what's important here to recognize is that the speed of the molecules on average increase roughly by the square root of the temperature. Okay, the more we heat up a gas, the faster the molecules are going to move on average. And we actually see this because when a person inhales helium, you got to be careful with this, folks. Don't inhale helium. You can you're displacing oxygen that you need to live, and normally it's harmless, but if you inhale too much helium, you can get yourself in a little bit of trouble. But you've seen when people inhale helium, their voice suddenly gets higher. Okay, how does that happen? Well, if you look at this equation right here, helium has a much lower mass. Okay, what is nitrogen? A nitrogen atom is atomic mass of 14. So a molecule, N2 molecule, is going to have an atomic mass of 28. Oxygen, is 16. So diatomic is going to be 32. So roughly, the molecular mass of air is going to be somewhere around 28, 29 if we average everything out. But of course, helium, its atomic mass is 4. Okay, so that m down here is much, much smaller, which is going to make the root mean squared velocity higher for a given temperature. Okay, now when I speak, the pitch of my voice is determined by a few things. First of all, my vocal folds, how thick they are, will affect the frequencies that are produced. But the other thing is the length of my vocal tract tends to amplify certain frequencies. So these are related to the wavelengths which match the resonances of my vocal tract. So V equals lambda times F if I increase this side of the equation, if instead of inhaling nitrogen and oxygen, I inhale helium, which makes V larger, the wavelength is fixed. That depends on the internal structure. So if V goes up, right? If I increase V, the frequency is going to go up. So inhaling helium actually makes the frequency of my voice higher. And that's that Mickey Mouse effect that we get by inhaling those. So again, a few important things that we saw here. Again, Newtonian mechanics leads us right to the ideal gas law, okay? We also see that the speed of the molecules on average is very much related to the temperature. And of course, the temperature is very much proportional to the average kinetic energy, okay? So those are the big takeaways from this section. And again, here we see RMS velocities for different gases. Hydrogen and helium, for the same temperature, they're traveling much faster. Remember, temperature is related to the average kinetic energy, right? So if you don't have much mass, you better be traveling faster to get the same kinetic energy. And then, of course, oxygen and nitrogen, their RMS velocities are, high 400s, low 500s, around 20 degrees Celsius. Here's something important to remember, however. The RMS speed is always higher. It's always greater than the average speed, okay? It's just, mathematically, that's the way it happens. So the RMS speed is probably a better way to relate it to energy, whereas the average speed is a better way to relate it to the speed of sound. So even though our RMS speed for nitrogen is about 511, the speed of sound is closer to about 450 meters per second. Okay.